This is a Cambridge IGCSE Physics Paper 2 multiple choice talk through from June 21. Number 1. The diagram shows a stone of an irregular shape. Which property of the stone can be found by lowering it into a measuring cylinder half filled with water? So here's our measuring cylinder. And remember, a measuring cylinder measures volume. So if our original water level looked like this, then we drop the stone in it. That water level will rise, and the difference between those two numbers will be the stone's volume. Which row describes speed and velocity? So speed is a scalar quantity. It has magnitude only, whereas velocity is a vector quantity with both a direction and a magnitude. So B is the answer. 4 balls with different masses are dropped from the heights shown. Air resistance may be ignored. Which ball has the smallest average speed? Personally, I don't think you need to do any sums in order to work this out. The ball being dropped from the lowest height will therefore gain the lowest speed, despite the fact that it's the heaviest here. So the answer here is A. An object of mass 2 kilograms is taken from the Earth where the gravitational field strength is 10 to the Moon where the gravitational field strength is 1.6. Which row is correct? So we're looking for the weight on the Earth and on the Moon, so you need this equation, weight equals mass times gravity. So let's do on the Earth first of all. We know its mass was 2, its gravity was 10, so that becomes 20 newtons. On the Moon, using the same equation, the mass stays the same on the Moon, but we've been told the gravity is 1.6. So these are the correct answers, D. The mass of an empty flask is 34 grams. The volume of liquid added to the flask is 20 centimetres cubed. The total mass of the flask and the liquid is 50 grams. So what does that mean in terms of the liquid's mass? Well, it's the difference between 50 and 34 grams, so it's 16 grams. And then we're being asked to find the density. So remember, density equals mass divided by volume. So that's 16 divided by 20, which is 0.8. The extension load graph for a spring is shown. The unstretched length of the spring is 17 centimetres. When an object is suspended from the spring, the length of the spring is 19.2 centimetres. What is the weight of the object? So let's work out the extension. It's the difference between 19.2 and 17 centimetres. So that's 2.2 centimetres. So look along this part of the graph line, then read down to the x-axis, and we can see that the weight, remember weight and load have the same unit, is 3 newtons. A cart has a mass of 10 kilos. A boy pushes on the cart horizontally with a force of 50 newtons. The cart accelerates at 0.5 meters per second squared. What is the frictional force acting on the cart? So let's first of all start by working out acceleration, which is force divided by mass. So our force is 50 newtons, our mass is 10, so we have an acceleration of 5 meters per second squared. We've been told that the cart accelerates at 0.5 meters per second, and we know that the frictional force will be acting in the opposite direction, so we can therefore work out the acceleration in the opposite direction, which is the difference between the acceleration we calculated and the one they've given us, which is 4.5 meters per second squared. And then lastly, to find that force is mass times acceleration. We know the mass was 10. The acceleration we've just worked out is 4.5. So our answer is 45 newtons. A ball has a mass of 2 kilograms. The ball approaches a wall at a speed of 3 meters per second and rebounds at a speed of 1 meters per second. What is the impulse on the wall? So impulse equals change in momentum. What's our initial momentum? Remember, that's given by mass times velocity. So that's 2 times 3 equals 6. Our final momentum notice that it's rebounding, so we've got the same mass, but our speed is -1 to get -2. And therefore our impulse is our initial momentum minus our final momentum, so that's 8. And the units are NS. D. Which situation involves no work being done and no energy being transferred? A car skidding to a stop on the road. That's not true in this case. A crane lifting a load, definitely lots of work being done there. A heavy load hanging from a strong bar. Yeah, no energy is being transferred or no work's being done there because it's just static. A student dragging a big box over a rough floor. Students doing lots of work there too. The answer is C. A student suggests that there are several ways of transferring energy to a small stationary block of iron on a smooth table. He makes the following suggestions. Heat it. Yep, that's a good way of transferring thermal energy. Shine a light on it. Yep, that's certainly a way of transferring energy. Pass a current through it. Yes, again. Because remember, passing a current has the effect of causing a heating effect. So which suggestions are correct? It's actually all 3. An engine produces 240 kJ of energy in 2 minutes. What is the power output? So I'm using We Play Tennis to help me here. So power is work done over time. Our work done is 240. No need to change the units because all our answers in terms of kilowatts. Our time, we do need to get that into seconds. So 2 minutes is the equivalent of 120 seconds. So we've got 2 kW as our answer. A book has a mass of 400 grams, so that's 0.4 kilograms. The surface of the book is in contact with a table that has dimensions of 0.1 meters by 0.2 meters. Gravitational field strength is 10. What is the pressure exerted on the table due to the book? We want FAP here, where pressure equals force over area. We need to get our mass as a force, as a weight. So we do 0.4 times 10 to get 4 newtons is our weight and our force. Our area is 0.1 times 0.2, which is 0.02. So 4 divided by 0.02 is 200. The diagram shows a mercury barometer, at which point is the pressure greater than the atmospheric pressure. Remember, pressure increases at depth. So go straight for D here. The table gives information about molecules. Which row describes a gas? So remember, in a gas, we've got our molecules moving around very quickly. The molecules are far apart, and the forces holding them together are very weak. Negligible means extremely small. So the answer here is C. Very small pollen grains are suspended in water. A bright light shines from the side. When looked at through a microscope, small specks of light are seen to be moving in a random jerky manner. What are the moving specks of light? Remember, this is a representation of Brownian motion. It's actually due to the pollen grains being hit by water molecules which are exerting a tiny force to help move them. Why are small gaps left between the metal rails of a railway track? Okay, that's because temperature changes will lead to either an expansion or a contraction. Now, the gaps mean that we're expecting an expansion, and that comes from things getting hotter, so the rails getting hotter because the particles take up more space as they're vibrating more. A block of metal absorbs 2,000 joules of thermal energy. The temperature of the block rises from 10 degrees to 20 degrees. The mass of the block is 2 kilograms. What is the specific heat capacity of the metal? We need this equation. Q equals mc delta T. Q is energy, so that's been given, 2,000 joules. Mass we've been told is 2 kilos. We're after the specific heat capacity C. And then the difference between 10 degrees and 20 degrees is our change in temperature, so that's 10. Do 2,000 divided by 20 to find C. So our answer is 100. Which statement about boiling and evaporation is correct? Boiling requires a supply of thermal energy, but evaporation does not. That's false. They both require a supply of thermal energy. Evaporation takes place at the surface of a liquid, but boiling takes place throughout the liquid. Yeah, that's actually the main difference between evaporation and boiling. When water boils in a kettle, its temperature decreases. That's clearly false. When water evaporates, its temperature increases. No, it decreases. The answer here is B. A metal rod is heated at end X. Why does end Y of the metal rod become hot? So this is a question about conduction. So when the heat is applied here, the positive metal ions start vibrating more, and then the electrons which are delocalized within the metal are free to move. And it's the combination of these two things which will transfer that heat to end Y. So if we look at the options, A, energy is transferred from end X to end Y by vibration of positive ions and by the movement of electrons. Yes. Everything else is just saying one or the other. 2 square sheets of metal P and Q are heated to the same temperature. The metal sheets are shown. Sheet Q is emitting more radiation than sheet P. So this one is greater than this one. Which statement explains this? Now, if they were the same size, hopefully you know that P would be emitting more radiation because black is a very good absorber and emitter of infrared radiation. So the fact that sheet Q is emitting more radiation than sheet P means that option A, dull black surfaces, are better conductors of radiation. That's true, but it's not the reason why Q is doing a better job here. Dull black surfaces are better emitters of radiation. Again, that's true, but not the reason why Q is emitting more radiation. The surface area of Q is larger than that of P. Yes, 40 versus 20. So although black is better, the fact that we've got so much more of Q explains why it's emitting more. White surfaces are better absorbers. No, they're not. They're better reflectors. A water wave passes into a region where the waves travel more slowly. As it passes into the slow region, what happens to the frequency and what happens to the wavelength of the wave? So this is our wave equation. Wave speed equals frequency times wavelength. Now, we can't do anything about how many waves there are, so the frequency. So there's no change there. But if they're getting slower, that must mean, therefore, that this value here is decreasing. For V to be slower, this value must have decreased. So that's just maths. So we've got no change and the wavelength decreases. The answer is C. Light travelling at a speed of 3 times 10 to the 8 metres per second strikes the surface of a glass block and undergoes refraction as it enters the block. The diagram shows a ray of this light before and after it enters the block. What is the speed of light in the glass? So the first thing you want to do, hopefully, because you can see here you've got an angle of incident and an angle of refraction. We want to work out the refractive index using this equation. So you'll get n, the refractive index, equaling 1.5. And that tells us that light is travelling 1.5 times faster in air compared with the glass. Remember, it always slows down as it enters a denser medium. So to work out the value of that speed in the glass, we do 3 times 10 to the 8 divided by 1.5 to get 2 times 10 to the 8. The diagram shows a narrow beam of light incident on the glass-air boundary. Some of the light emerges along the surface of the glass and some is reflected back into the glass. Which row is correct? Now, the fact that that ray is passing along the boundary means that our angle of incidence must be the critical angle. So that means that theta sign is the critical angle. The next thing to ask ourselves, is total internal reflection taking place? Well, it's taking place here, but obviously this is refraction along here. So no, it's not taking place, which is why A is the answer. An object is placed in front of a thin converging lens. The diagram shows the paths of 2 rays from the top of the object. An image of the object is formed on a screen to the right of the lens. How does this image compare with the object? Okay, let's create an image arrow. So we'll just carry these rays through the lens. And where they cross is where the image is formed. So we'll draw an arrow for that image. So we now need to make a comparison between this arrow and the object one. Hopefully you can see that it is longer, which means our image is bigger, and it's also upside down, so it's inverted. So it's larger and inverted, A. A remote-controlled vehicle is travelling on the surface of a planet. The vehicle senses an obstacle ahead. It sends a radio message to the control room where it's being controlled. The control room is 2.4 times 10 to the 6th kilometre away from the vehicle. The control room sends a message back to the vehicle telling it to stop. What is the minimum time that elapses between the vehicle sensing the obstacle and receiving the message back from the control room? So the first thing we need to do is know that the speed of light is 300 million meters per second, which is the same as, let's get our units all the same, 3 times 10 to the 5 kilometers per second. Our distance is double this number just because it goes there and then comes back again. And then time, remember, is given by distance divided by speed, which actually equals 16 seconds. A sound wave is travelling outwards from a loudspeaker into the surrounding air. Here are 3 statements. The air pressure is lower at a rarefaction compared with undisturbed air. The density of the air is less at a compression compared with undisturbed air. The distance from a compression to a rarefaction equals half a wavelength. Okay, I'm going to try and draw this for you, probably quite poorly. So here's a compression area, rarefaction, compression area, rarefaction. Okay, that's enough of that. Compression, 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 rarefaction. And then let's try and line it up. So what can we work out from my appallingly drawn diagram? The air pressure is lower at a rarefaction compared with undisturbed air. Well, you're sending a sound wave, so this is actually true. The density of the air is less at a compression compared with undisturbed air. No, wherever there is a compression, you've got quite a high density in comparison to undisturbed air, so that's false. The distance from a compression to a rarefaction equals half a wavelength. I know this is abysmally drawn, but if you look at here from your compression to your rarefaction, hope you can see that's half a wavelength, because a full wavelength would be from one compression to the next. I'm not even sure my picture helped, but the answer here is B. The sound from a loudspeaker must pass through 2 materials to reach a microphone. Which combination of materials gives the shortest time for the sound to reach the microphone? Remember, sound travels fastest in solids, simply because the particles are closer together. So we definitely don't want gases. And then we're now comparing C and D, solids versus liquids. We always want the solid, so the answer here is C. Diagram 1 shows a small compass needle with its poles marked. It is not near any magnetic materials. Diagram 2 shows a bar magnet with its poles marked. The compass needle is placed at point P. So down here, this compass needle will be placed. In which direction will the end pole of the compass needle point? Remember, opposite poles will be attracted, so therefore it means that this compass will be pointing to the south, to the right. A student rubs a plastic rod with a cloth. The rod becomes positively charged. What has happened to the rod? Remember, you're only going to be transferring electrons by friction here. And electrons have a negative charge, so if the rod becomes positive, it must have therefore lost electrons. An isolated metal sphere is positively charged. It is then brought near to another isolated metal sphere that is neutral. What happens to the charges on the neutral sphere as the positive charged sphere is brought close to it? Now, the positive charges can't move. Remember, I said it was all about negativity moving, but they'll be moving to the left where they'll be attracted. So the answer here is D, because the positive charges do not move, the negative charges move to the left. Which statement about the resistance of a metal wire is correct? So we're looking at resistance as well as the length of the wire and the cross-sectional area. This is something you'll just have to learn from me, but the resistance is directly proportional to the length of the wire and is inversely proportional to the cross-sectional area, which means that as the wire gets longer, the resistance increases, but as the area of the wire increases, the resistance decreases. The circuit diagram shows an LDR in a potential divider. A voltmeter is connected across the LDR. So there's your light-dependent resistor. Which row shows the resistance of the LDR and the potential difference shown on the voltmeter at a specific light level? So the first thing to be aware of with an LDR is that as light intensity increases, resistance decreases. So this is correct. If it's bright, then the resistance is low. If it's dim, then the resistance is high. So we can get rid of B and D immediately. But now we need to narrow it down between A and C. Notice you have a series circuit here, which means that the current is the same everywhere, whereas the potential difference, the voltage, is shared. And that's important if we consider if the resistance is low in the LDR, then what holds true is the fact that the current is constant, but according to the equation VIR, it therefore means that the potential difference, the voltage, is also low. If the resistance is high in the second scenario in the LDR, so if we're in dim light, current is still constant. According to the equation V equals IR, the potential difference must therefore be high. And so if we follow this along, we know that the dim light levels meant that there was a high resistance in the LDR, and therefore we've just worked out that the potential difference would also be high. So the answer here is C. Logic gates are no longer part of the new specification, so we'll skip over that one. 34. A solenoid is connected to a very sensitive ammeter. A rod is inserted into one end of the solenoid. The ammeter shows that there is a small electric current in the solenoid while the rod is moving. Which rod is being inserted? So we need a rod that can have a magnetic field around it, so something like steel, nickel, cobalt, so that the magnetic field lines around the solenoid can be cut. So if you look down, we're not interested in copper, nylon, or uranium. This is all to do with magnetism and the generator effect. The diagram shows an electric generator with the coil in a vertical position. Which row describes the generator? So we know that we have these split rings and brushes which will help to turn that coil continuously, which will be creating an alternating current. So it's between A and B. Because it's a generator, remember the magnetic field lines need to be cut. And if that coil is in a vertical position, those north-south magnetic field lines will not be being cut. They'll just be passing straight through the coil. So actually it's when the coil is vertical will the output be zero because there are no magnetic field lines being cut. The diagram shows a transformer. There are 460 turns on the primary coil, 24 on the secondary coil, and the primary voltage is 230 volts. What is the secondary voltage? So you need this equation, number of turns on the primary divided by number of turns on the secondary equals voltage primary divided by voltage secondary. So let's substitute in the numbers we've been given. Number of turns on the primary is 460, number of turns on the secondary is 24, voltage primary is 230, and we're after the secondary voltage. So do this side of the equation first of all, 460 divided by 24, and then take that number and do 230 divided by it to find that X equals 12 volts. The charge on a proton is E. What is the charge on an electron and what is the charge on a neutron? A neutron is always neutral, which means it has no charge whatsoever. So we're picking between B and D. It's a bit weird that they've said that the charge on the proton is E. However, it's fine because we know the electron has an opposite charge, so we're just going to say that it has a minus E charge. I know this sounds a bit unusual because obviously an electron is normally negatively charged, but we're going with what they've given us in the question. The answer here is D. 4 students are asked to comment on the processes of nuclear fission and nuclear fusion. Their comments are recorded in the table. Which row is correct? Remember, nuclear fission is when a neutron is absorbed by the nucleus of something like uranium, and then the nuclei splits, forming 2 smaller daughter nuclei, and the release of energy. Whereas nuclear fusion is all about taking two heavier nuclei, causing them to be fused together, and then there's a loss of mass but also a release of energy. So if we look at the options, fission, energy is absorbed, nope. Fusion, a large unstable nucleus splits, nope. That would be a fission answer. If we actually go down and have a look, we've got energy being released and two light nuclei joining, so D is the correct answer. Radon 21986 decays by emitting an alpha particle. Which nuclide is formed in this decay? So an alpha particle, remember, is 2 protons and 2 neutrons, which means that our new element will have a mass number of 4 less than before, so that will be 215, and then it's lost 2 protons, so our atomic number goes down to 84, and that's because 2 protons and 2 neutrons have been given off, so we can see that's happened here. Polonium A. The graph shows the activity of a radioactive source over a period of time. What is the half-life of the source? So that's when the count rate drops to half of the original amount, so down to 60 in this case. Read down to the x-axis and we can see that the answer here is 2 minutes B.